So let's start. First of all, thank you all for coming. Thank you to DataEngConf for hosting us. So I'm going to talk a little bit about how Spotify distills terabytes of data into meaningful music recommendations. And it works. A little bit about Spotify. Spotify has over 140 million active users. We've over 30 million songs on our service. Users have created over 2 billion playlists, and we're currently available in 61 markets. So, a little bit about me. I've been at Spotify for 6 years now, so it's been a while. It's been awesome. I'm currently an engineering manager here, where I focus on data and backend. I have a background as a technical product manager at Spotify, and I started out as a data and backend engineer. Some of the projects I've worked on previously was Radio, our initial free tier, Discover page, which is the precursor to Discover Weekly. I had switched off that project though before it became Discover Weekly, so missed out a little bit there. Worked on Spotify Running, and last but not least, What Not to Recommend, which often is could be a more important problem than what to recommend. You could have your best radio, and then a Christmas song comes on, or a song with talking in it, or an intro or an outro. So it's actually very, very important to make sure that you don't kind of get people out of their flow. Karaoke songs, could be whatever. So today, I work in a squad, with a squad, which is Spotify speak for a team, called Inferno, which is short for Inferred Knowledge. Spotify is then organized into tribes, so of course we have to have a tribe called Quest. Spotify likes puns, and we're part of the user engagement mission. And here's our mission statement. The main thing is that we want to present the right content to the right user at the right time. So we build a lot of the underlying data sets, services, models that teams like Discover Weekly, Daily Mix, Radio then use to build their features on top of. So we don't own any outward-facing features. So in February 2016, Spotify made a public blog post saying, hey, we're all in with Google's cloud solutions. Previously, we had our own data centers. We have 4 data centers. One of them has actually recently been shut down. And we did everything on our own hardware. But we said, we think it's the right time now to switch over to the cloud, and we went with Google. Initially, it was a lot about just, okay, instead of having bare bones machines, let's just use VMs. But we very quickly started getting into leveraging the more advanced technologies that they had. So Spotify has always been very big on Hadoop, using MapReduce. We started switching over into Shio. Shio is a Scala framework that was created at Spotify, and it's open source. Check it out. It's very, very cool, I think, for writing Dataflow pipelines. We're also using Google's Dataproc, which is their hosted version of Hadoop. Instead of hosting our own Cassandras, we said, well, let's have Google manage that, switch to Bigtable. Instead of building up our own storm topologies, let's use streaming Shio, which also gives us the benefit of that it unifies the streaming and the bash models, which means a lot more code sharing. And instead of storing everything in HDFS, let's store stuff in GCS, which is basically Google's cloud storage buckets, or in BigQuery. So let's go. So what are we talking about today? We're going to focus around 4 different questions. So the first question is, has the user heard this song? The second question is, does the user like this song? The third question is, which songs would this user like? And the final question is, hey, we have a lot of audio. What can we learn from it? And using these 4 basic questions, you can actually build a lot of features on top of it. For example, you want to build Discover Weekly. You say, okay, well, what are some songs we think this user would like? But it's discovery. So let's filter out what they've heard. If it's a daily mix, we want stuff that we know that they love. So let's grab some of that. Let's get some stuff that we think they like, and so on. So these are very much the building blocks that kind of go into a lot of features. So let's go. Has the user heard this song? In this case, we're talking about listening history. Basically keeping track of everything that a user has heard. This thing has to be in real time. We can't have a server where somebody asks us, oh, has this user heard the latest Justin Bieber song? And we say no when they listened to it 5 minutes ago. They may have listened to it in incognito mode. I don't know what we should say then, but. And this is a lot of traffic, which makes it a very interesting problem. We can top out at over 100K events per second that we need to ingest. So what does this look like? Well, we have our Spotify clients. They're all connected to web gates or access points, APs as we call them, which is basically the main entry point into Spotify from the outside world. WebGate will then push all these messages into Google's pub sub, where anybody within Spotify that is building a feature can tap into. So you can say, I want to hear when, I want an event for when a song has finished playing. I want an event for when somebody added a song to a playlist. I want an event for when somebody logged in, when somebody logged out, when somebody registered, and so on. In this case, we're interested in when a song has finished playing. The endpoint of this pub sub is hooked up to a streaming Shio job that we run in 3 different data centers. So Spotify has services in 3 locations, in Asia, US, and Europe to minimize latency. And these are all in Google's data centers. So we have this streaming Shio job. We take the data, transform it, and write it into 3 different big tables, 1 in each location. And off of that, our feature teams can then call our listening history service, which reads the data from Bigtable. And this whole chain, they might have a lag of a few seconds. So pretty quickly after something has finished playing, we will be able to tell other teams at Spotify, say, hey, this user has heard this song. A little bit more about Bigtable, which is the storage that we picked for this. Bigtable is a key value NoSQL system, basically, which means that the basic building block you have is you have rows and you have columns. And you can kind of think of both as indexes. It's very quick at doing individual row lookups or scans along the columns. But it doesn't really have any other, you can't put additional indexes on it. It can't do aggregations for you or anything like that. So it's very simple, but it's extremely, extremely scalable. Also, one amazing thing with Google Bigtable is you can size it up as down as your needs go. So a default Bigtable, when you create one, is 3 nodes. If you want to do a huge ingestion job, you can scale it up to 30 nodes. You wait a few minutes for everything to kind of stabilize. You run your enormous job, data is in there. You might wait a little bit more, and then you scale it back down again. Which allows you to basically get capacity on demand, while, for example, with a Cassandra, it's a lot harder to add and remove capacity. So talking to Bigtable uses gRPC, which is, I guess, Google's version of RPC, uses protobuf. It's nice to use, but it's kind of complex filling out protobufs. So Spotify has created a client that we call Simple Bigtable Client. Sometimes we're not very good with naming. That we've open sourced, that we actually use extensively internally. One very interesting feature of Bigtable that we take advantage of is that you can have multiple versions of a column. So you can, instead of just having your rows and your columns, you can actually stack multiple values within a different column. So we take advantage of that. And actually, in this case, we only have, for each user, we have user has 1 row, and we stack all of his plays in 1 column. And this gives us very nice features where we can say, give me only data with its certain timestamps. Only give me the last X number of records, if somebody wants to say. What are the last 10 songs this user has heard? It also allows us to filter on the actual value in the columns. So we can send in regexes to say, hey, this artist, this column, maybe this playlist, and so on, and offload all of that data into Bigtable. We store 90 days worth of plays, using up around 30 terabytes of data. And so far, it's been working really great. We've had this in production for, I guess, 4 or 5 months moving on, does the user like this song? So listening is not the same as knowing. It's not the same as liking. If you've heard a song once, yeah, you listen to it, you may or may not know it. If it played on radio 2 months ago and I said, hey, I know you know this song, you might say, what are you talking about? I don't remember it. Knowing a song definitely is not the same as liking a song. So we try to model what does it mean to like a song. Well, context matters. If you add a song to your own playlist, you set it on repeat once, you play it over and over again, it's a pretty strong signal that you like the song quite a bit. You know, if you get the song and if you skip over it, if you consistently skip over it, maybe you don't like it as much. Also, how long ago did you play it matters. We provide datasets over windows of 28 days, 6 months, and all time. Initially, we started out with kind of like magic weights, saying, look, well, if you heard it in your own playlist, you get a multiplier of 2. If it came on radio, you get a multiplier of 0.1, and so on, which was not very scientific. So we actually, earlier this year, created a survey that we sent out to a couple of 100,000 users and say, hey, do you want to rate a couple of songs that we think you like? And then, it looked like this. They got a song that we knew that they've heard, and we said, what do you think about it? And we didn't pick the absolute top. If you've heard a song 1,000 times, we're gonna assume that you like it. But we picked like a little bit further down. And we got some great feedback on like how much recency matters, how much does the song map up with your normal taste, and so on. So it actually allowed us to build a better model on where plays should come from, and how we should treat individual plays to model if somebody likes a song. So on the far side is how we used to do it in the old days. All data which we store in HDFS, which is the Hadoop file system. We would then have a crunch job, which is a Java wrapper around plain old MapReduce. We would read up all the data, which could be dozens and dozens of terabytes. We would take today's plays and merge them in, and then write out everything again, which pretty much means that every single day you're copying 99.9% of your data, changing a couple of rows, and then writing them back again, which was extremely taxing on our Hadoop cluster, and just not very efficient because data hasn't changed. In today's world, using Shio and Bigtable as the storage for the underlying data, we're able to take in today's plays, just mutate the rows that are actually relevant, and then write them straight back to Bigtable. Using this is still a lot of data. It's over 200 terabytes of data. So we have a 250-node Bigtable cluster. This is still, today for us, quite big, so we're not doing it in real time. We're doing it batch, basically we're calculating it up daily, which in this case we feel is probably good enough. If you've heard a song a couple of times in one day, we may not be able to say that you like it. But if you've heard it over a couple of days and so on, then we're more confident. We run some Shio jobs on top of that, just calculating deltas and just store the changes back, which has the resource utilization has gone down tremendously with this. We output the final scores to GCS, to BigQuery, where our analysts can go to work, or feature teams often use BigQuery data as inputs into their pipelines. And we also ship it off to separate Bigtables in our 3 data centers, where services can we have a service that can tell you how much you like a song, where feature teams can hit it in real time. Which songs would this user like? So we can look at this as 2 separate problems. The first problem is a ranking problem. Say, I have a user, I say I have 100 songs, or 100 playlists, or 100 artists. And you say, can you put them in order for me? Basically, put the ones you think the user will like first. And then at some point, maybe tell me that everything below this, user probably doesn't like. Versus discoveries, you say, hey, out of all the artists that we have, out of all the tracks that we have, what are some good candidates to give to this user? We look at these problems in the same way. We just think about discovery is of ranking from an extremely long list. It could be ranking among 30 million songs. We're not going to return all the 30 million songs for you, but we're going to rank the head of it and give it back to you. So for this, we need some way to come up with distance metrics between songs and users and any other entity that we have. So one hypothesis that we have, which probably is not too far out there, is if songs often show up in the same playlists, they're probably related. So, and we have 2 billion playlists that our users have created, so let's just use them. So what do we need to do? Well, we need to sample some good playlists. A good playlist is a playlist that has more than a song in it. A lot of playlists just have one album. We want some variety. We want a minimum number of artists. We want a minimum length. We don't want to take too many playlists from a particular user and so on, but we want a nice, good sample. We want to mitigate feedback loops. Spotify creates a lot of playlists for our users. We create Discover Weeklies, Release Radars. We have a lot of algorithmically generated playlists for artists and so on. We don't want to train on them because a lot of them come from our own data. Then we just keep feeding back that say, hey, whatever you did was great. Keep doing it. And I cannot understate the importance of not recommending Christmas and children's music. No matter what you do, no matter what people listen to, what type of music they like, come Christmas, everybody listens to Christmas music. And there's obviously a lot of people playing music for their kids, but then they still get very upset when we put Moana in their Discover Weekly. So how do we go about this? We use Scalding, the MapReduce framework, running on Dataproc. So this job we didn't rewrite in Shio yet. We just lifted it over to generate the training data, basically going through all the 2 billion playlists we have, generating a smaller set. We then ship this off to one single large machine where we let it run for a couple of hours on end, and it spits out a vector model that gives us distances between individual tracks, albums, and artists. We get albums and artists out by, and a playlist is usually normally tracks. We randomly switch out every once in a while the track for the album it's on or the track for the artist it's on. And that way we're able to get all these 3 entities into the same vector space. We then roll up the track vectors into playlist vectors. Today actually using simple averaging. The playlist vector is the average of the vectors within it. User vector is a weighted average of what the user has recently played. So if you notice, if you're binging on a certain type of music one week, your Discover Weekly will definitely be different the next week. And we also provide real-time user vectors, which is very short-term using the listening history service we had, which if you go to the homepage on Spotify, you can often see that it switches very quickly based on just what you've listened to. And then we then make this data available in a multitude of ways. One thing I want to call out is we call annoy trees, which are approximately nearest neighbors. Oh yeah, is the name of it, which is a nearest neighbor library that we've created here at Spotify. It's also open source, available on GitHub. It lets you build a data structure where you can throw in 30 million vectors, and you say, okay, I want the 1,000 vectors that are closest to something. So it very quickly let you pull out candidates without brute forcing everything. So how does this work for the users? Well, they call into a service that we call ranking. If they want to discover among all tracks at Spotify, among all artists, we call out to a nearest neighbor service. If they want real-time data, we call out to the listening history service we talked about a bit before. We do a lot of ranking of editorial playlists. On the Spotify homepage, there's a lot of recommendations for like, hey, here are some playlists for you to jump into, or check out this stuff. We call those content pools, where we have playlists for specific activities, or playlists for certain artists, and so on. Because they number in less than a couple of thousand, or I think less than 20,000, we just brute force the calculation. It's fast enough. And whenever we need the actual underlying vectors, we have a service that you just use is backed by Bigtable. to just give us back the underlying data. The content pools are small enough, so we decided to go with data store because then we don't really have to think about how we store the data and anything like that. And it also doesn't sit on the critical path, so we can get away with we can get away with it. Excuse me. So, what can we learn from the audio? Today, previously, we've just used user behavior to model what we create. But there's a lot of great signal in the audio. We can have acoustic similarity saying like, have a song. What songs sound similar to this? And acoustic similarity is actually really interesting to play around with. If you use similarity within we call the normal vector space, if you pull an artist and you pull, say, the 10 nearest neighbors, it's probably going to be the same genre. Probably if you know one artist, you're probably going to know most of the other ones, similar popularities, and so on. If you pull stuff by acoustic similarity, chances are you've never heard of these artists. It doesn't have any bias towards popularity of the item that you picked. It doesn't care that much about genres or language or anything like that. But once you listen to it, you're like, okay, yeah, it makes sense. But it's a very interesting experience. Then we can also pull out data such as key, tempo, where all the beats are, if the song has silence, if the song has speaking, which is important for not recommending songs that have too much of that. Actually, all of these features, except the first one, is available through our public API. So feel free to play around with all the data we have. We give it out for all of our tracks. Here we have a little bit of a similar approach. We store all the derived data into Bigtable. We have a SHIO job to detect new content coming in. New content comes in daily on Spotify. We need to process it as quickly as possible so that we can make sure it shows up in recommendable surfaces. Whenever new audio comes in, we send it to a RabbitMQ, and then we'd have Python workers that pick this up, downloads the audio, does whatever it needs to do. It could be acoustic fingerprinting, it could be just analyzing the audio, figure out where the downbeats are, and so on. And from there, we have a SHIO job for generating the audio attributes, which are the key and the tempo and the mode and the energy, which is a mishmash of all kinds of different algorithms. And then we make this data available in pretty much all sources that we have at Spotify. Audio also helps us with a very important problem, which is the cold start problem. All the other sources we talked about earlier requires us to have some data. Until enough people put a new track into good enough playlists, we won't be able to recommend this song. Which means that when Taylor Swift drops her latest song, it can't go out right away. We want it to show up in people's release radar the next day. So what we can do is we can analyze the audio of any new tracks that come in, use that together with some other metadata that we know. If we know about the artist, we have some data. We could look at the country it came from and so on, and then try to map that into the standard vector space, which means that as soon as content is available, we're now able to recommend it. So, in summary, here's a list of all the different technologies that we're using. We've started to heavily leverage all the Google technologies. Some of them, like SHIO, Annoy, and Luigi, are our own. Luigi is a dependency management framework that we also have open source that we're extremely heavy users of. And yeah, so far, the change-up has been great. Completely switching over our platform has given us a great chance to kind of go back and rethink how we've been doing things. Saying, well, do we want to just forklift this over, or is it a chance for us to kind of rethink how we're doing? It's opened up a lot of opportunities for us to do a lot more stuff in real time. Now with SHIO, we're able to merge real-time and batch processing, which has been extremely, extremely helpful. And it's been a little bit painful, but overall it's been a great journey. And that was all I had. Thank you very much. Any questions?
To tables, oh sure. For your users recently listened to tables, you said you have one in Europe, North America, and Asia. Are those all are those replicas, or are they only for users of that region?
Users normally connect to the data center that they're closest to, but not necessarily. We could, for example, take a data center down for maintenance, or if we have any kind of problems. So we cannot assume that users will always be in one data center, which means that we basically any song that comes in, we push it to all 3 data centers. Bigtable currently does not have replication between data centers. They're opening up replication within a data center, which basically means that you can now have one Bigtable for your service calls, and then a separate one that you, for example, run your reporting on. While in our case now, we have to be a little bit careful when we run ingestions and reporting to scale them up and down so that we don't impact the latency of our services. But hopefully, cross data center replication is coming in Bigtable, and we will jump on that when it comes.
Cool. Thanks. One more. How do you deal with? Is there a problem with increased latency when a user goes traveling outside of their normal database region?
No. Spotify uses a DNS to find you the closest data center.
Hi. I had a question for you over on this side.
Oh, hey, sorry.
It seems like you've made a big move away from, say, Spark, using Spark as your core sort of runner of the jobs onto Cloud Dataflow, which I understand is, I'm on Amazon, so I guess I don't get to play with the Google toys, but based on an Apache project, that Apache Beam, how do you find working with almost a completely different interface, or did you, from what I understand, you used Skyo to kind of almost abstract some of those details away? What were some advantages of moving to, say, Cloud Dataflow over just running on core Spark?
So actually, most
core MapReduce, really, actually.
Yeah, so we were actually not extremely heavy users of Spark beforehand. We were mostly using MapReduce. I think the main reason was that let Google handle the management of workers or anything like that. We do have a tool called SP Hydra, I believe, that we've open sourced to kind of let you easily create and tear down Hadoop clusters. But we figured that, no, let's just kind of abstract all of that away. And Shia was written very much looking at Spark and at Scalding, making the transition very easy for us. And I think so far, it's been a very good transition. We've definitely had a little bit of growing pains, but Google has been very open in working with us. So the question is growing pains, if there's anything that we found harder now than before. Well, sometimes when things do go wrong, it's very much a black box. So, if you're having some kind of issues, your Bigtable is performing erratically or something, you really have nowhere to go. Google there has been very open in kind of helping us out, and they also have been building more tools for monitoring and kind of looking into it. But it definitely has been scary, but I feel like we have a lot of data. Google has a lot more. So, any problems we run into, we're pretty confident that they've hopefully already seen.
You talked about the vector space, so I'm wondering how do you normalize with different inputs? Like if you have different attributes or features or whatever you want to call it.
Oh, so the inputs are just the playlist under content.
And you talked about the mishmash for the different attributes between SVN and neural networks.
Sorry for that. So that is it's just different models. So for example, we have a model to calculate how much speech a particular song contains. For that, it's actually a voting between two SVMs. I don't know why they have two to vote, but while for some others, neural networks. So it's more each individual attribute like energy, valence, and so on, are calculated by different methods. So they're independent.
Thank you.
Mm-hmm.
Hi. Have you guys thought about how Discover Weekly may influence a user to move a song into a playlist with another song and then create a kind of feedback loop, and where the model is almost training itself or influencing the kind of organic environment you guys are aiming to model?
It definitely is something we think about, because the more we help people discover music, the more music they're going to listen to and save that we have. So it is a problem, or it's something we think about. We think today enough people create playlists, but as we're going forward, it's definitely something that we have to start thinking about more. It's like, what other signals can we use to not just get this feedback loop going over and over.
Hi. I was wondering if you could talk a little bit more about your cold start problems, in particular, not with just songs, but also your users. Like, if you have a brand new user, how do you sort of get recommendations out for him or her? And in addition, you sort of talked about listening versus actually liking, and how there's a delay between like listening for a day versus listening for a longer period of time. So yeah, if you could just address those.
Yeah. So the cold start problem with user is basically we know nothing about the user. We might know, or we may or may not know some demographic data about them, but that's about it. So often when users go on board, we ask them to go, when they join Spotify, we ask them to do a little bit of onboarding, maybe tell us a couple of artists that they like, a couple of songs that they like. Our goal is basically to get them playing something as quickly as possible. As soon as we have a couple of plays, we can now say, okay, at least you've listened to these couple of songs. Now we can recommend stuff for you. It may not be your true tastes, but at least you've actively picked something. But then some of our features are created in a batch fashion, so some of the things won't show up until the next day, or Discover Weekly might take you a week to get. So it is something that we're actively working on. Like, how can we get great music in front of new users as quickly as possible? And the other question was around. Okay, sorry.
Again, is there value in partial plays then?
There is value in partial plays. We look at skips. You can definitely have like a short skip and a long skip. The easiest model you can build on predicting skips is to say, did the user skip the previous song? And you're 90% accurate. So we definitely look at, if a user just sits and click, 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 it may not tell you much. But if they listen 20, 30 seconds into a song and then skip away, that may mean, okay, they give the song a chance, say, no, I don't like it, or I'm not feeling it right now. So we say, okay, well, that's kind of like a little negative signal. If they listen through most of the song through, we say, like, well, maybe the song has a long outro or whatever. Then we say, okay, it's good. So definitely the length of time until the skip matters quite a bit.
So you talked about kind of the identifying spoken word and those aspects. Is there any kind of NLP or processing on that going on for either like, this content isn't appropriate for children, or this song has puns in it, or like, I have a pun running playlist specifically. How do you, are themes or tropes or like other kind of things that you can get out of the actual lyrics in order to create more data?
So today, my team, we don't look at lyrics. I think there are other teams at Spotify that look at it. We're more looking, as of now, to just detect speaking in a song, to say, if there's too much speaking, should we get it out? We don't do like look for explicit words or anything like that. We do get explicit tags from the labels that we use. So if you, especially if you're a free user, every once in a while we have to kind of give you another song. But, so we definitely there take into account if all the songs you listen to are non-explicit, we're not going to give you an explicit song. But yeah, I would love for us to get more into like the NLP part, because I think there's a lot of signal in the actual lyrics.
So continuing on the same topic, the learnings that you get out of a listener's likability, is this knowledge shared with, let's say, music producers or outside industry, the music industry?
So Spotify has recently launched a Spotify for Artists app that artists can download, and they can kind of see, where their fans are, what they're listening to, and so on. I don't know exactly what data we share with them. If we share like skip ratios or things like that, but we're definitely giving them a lot more data to kind of get to know, your fans are over here, or you're this popular in these demographics and so on. So yeah, we're working quite a bit with artists, and it's just ramping up more and more.